Hi everyone, here we are back again to our chapter 18. We are talking about acid bases, right? And previously we learned about acid base definition, where we talk about if it is an acid, you need to have H plus ion in the form of hydronium ion, and then the hydroxide would be your base. Now let's look at this definition. It's Bronsted-Lowry acid-base definition. Now in this one it says acid is a proton donor. Proton is hydrogen ion, H plus. Acid is a proton donor. Any species that donates a H plus proton ion, which is an acid. Okay, so in Bronsted-Lowry acid-base definition, acid must contain hydrogen in its formula. Now, what is a base? Now, in the previous Arrhenius definition, we talk about a base is something that it has a OH group. Now, here it says a base is a proton acceptor. So, acid is a proton donor, and then a proton acceptor is your base. Okay, any species that accepts a proton ion, H plus ion. So a base must contain a lone pair of electrons to bond to H plus. An acid-base reaction is a proton transfer process. So for example, in the Bronsted-Lowry acid-base definition, acid is a proton donor. And a base, let's say base is a proton acceptor, and then the base need to have a lone pair. A base must contain a lone pair of electrons to bond to H plus. Remember, H plus, a proton is something that electron deficient. It doesn't have electrons. So the base should have a lone pair. Lone pair meaning 2 electrons. That is what needed to make a bond. So these 2 electrons given to hydrogen ion. So then with the 2 electrons can form a bond, and then that is considered as a base. Okay, so acid is a proton donor, base is a proton acceptor in terms of Bronsted-Lowry acid-base definition. So base accepts a proton. Now you can see it in this diagram how a water molecule acts as a base when hydrochloric acid is present. Dissolving of an acid or base in water as a Bronsted-Lowry acid-base reaction. Now this is your HCl. Remember, hydrogen is your donor, a proton donor. HCl is a proton donor, which is the acid. Okay, so this is the hydrogen and this is the chlorine. And this is your water molecule, oxygen, hydrogen, hydrogen, and the water molecule has 2 lone pairs. So water can act as a base because now the oxygen has a lone pair. It gives its lone pair to make a bond with the hydrogen. And then the bond between chlorine and hydrogen breaks. And the 2 electrons in this bond transfers to the chlorine. Okay, like this. So since there are 2 electrons, that goes to the chloride. Chlorine will become Cl minus. Okay, formal charge. And then the bond between lone pair of the oxygen and hydrogen forms here. Now what do we have? We have H3O plus. There are 3 hydrogen, 1 oxygen and a lone pair. H3O plus and chloride. So what is HCl here? It is a proton donor, and then the base is water proton acceptor. So water accepts a proton from the hydrochloric acid. Another example. Here you have ammonia and water. Now ammonia has lone pair. Ammonia lone pair takes up a hydrogen from the water molecule and form NH4 plus. Now here the base is ammonia, proton acceptor, and water here is the proton donor. So now it lost one hydrogen here. So it ended up having only one oxygen and one hydrogen, and with 3 lone pairs, hydroxide OH minus. So that's your hydroxide group. Ammonia is the base here, and then the water is the acid. Here, water is the base, hydrochloric acid is the acid. Now you can see the water can sometimes act as a base, water can sometimes act as an acid. Okay, remember, because in water we have hydronium ion and hydroxide both. So water can take up a hydrogen and become a hydronium ion, and water can lose a hydrogen and become hydroxide ion too. Sometimes it acts as a base, sometimes it acts as an acid. So the conjugate acid-base pairs. What are conjugate? Conjugate means linked acid-base pairs. So let's look at this reaction here. You have H2S and ammonia. One is going to be an acid, one going to be a base. And it gives you HS minus and ammonium ion. Now what happened over here? Who is going to accept a proton? So look here, H2S, HS minus. There were 2 hydrogens, and now you have only 1 hydrogen in H2S. It becomes HS minus, meaning H2S has lost a proton. If you donate, so losing means donating. If you lose a proton, if you donate, what is it? Is it acid or a base? It's an acid, a proton donor. So H2S here is your acid. H2S donates a proton to form HS minus. So H2S is your acid. And what happened to ammonia? NH3 became NH4 plus. Remember what happened to the number of hydrogens. There are 3 and there are 4 in ammonium ion here. Hydrogen number increased, meaning base is the proton acceptor. So ammonia is your base. H2S is your acid. Right? HS minus and ammonium plus. So ammonia accepts a proton to form NH4 plus. Now this is a reversible reaction. What happened in the reverse reaction? Go from HS minus to H2S. What happened to the number of hydrogen in this HS and H2S? 1 hydrogen here, 2 hydrogens here. So the number of hydrogen has increased. Meaning, what is this? Is it acid or the base? For the base, number of hydrogen increased because it's a proton acceptor. So in the reverse reaction, HS minus accepts a proton to form H2S. So it is the base in the reverse reaction. Right? What about here in the forward reaction? It is donating an electron, losing the number of, donating a proton, it's losing the number of hydrogens, so it is an acid. So in the reverse process, it's a base. What about the ammonia? Ammonia has 4 hydrogens here, 3 hydrogens here. So the number of hydrogens decreases, meaning it has donated proton, meaning ammonium ion is acid and ammonia is the base. In the reverse reaction, ammonium ion is the acid. Okay, ammonium ion donates to proton to form ammonia. Now we're going to link this to figure out what are our conjugate acid-base pairs. Here, the same thing I talked about in the previous slide, conjugate acid-base pairs, H2S and HS minus. Remember, they are related. They are related by the type of atoms they are attached. Only difference is they have differing number of protons. H2S, HS. So H2S and HS minus, we say that they are conjugate acid-base pairs. Now, which one is the acid? H2S is the acid because it's losing protons to become HS minus. So HS minus, if you look at the reverse reaction, it is gaining a proton, HS minus H2S. So in the reverse process, it's the base. So this is the conjugate acid-base pair. HS minus is the conjugate base of the acid H2S. So the conjugate acid-base pair in this case is going to be H2S and HS minus. Now in the case of ammonia and ammonium ion, ammonia and NH4 ion. They are the conjugate acid-base pairs. Ammonia is the base. Conjugate acid is ammonium ion. Okay, ammonium ion is the conjugate acid of the base ammonia. A Bronsted-Lowry acid-base reaction occurs when an acid and a base react to form their conjugate base and conjugate acid respectively. You see, acid 1 and base 1, base 2 and acid 2. So these are going to be your conjugate acid-base pairs. Acid-base, base-acid, conjugate acid-base pairs. Just like H2S plus ammonia and HS minus plus ammonium ions. Conjugate pairs in some acid-base reactions. So you can see here reaction acid-base, base-acid. So it tells you the conjugate acid-base pair. So this is the acid, this is the conjugate base. This is the base, conjugate acid. How do you know which one is the conjugate acid-base pair? You first figure out what are the like species, similar species, but their number of hydrogens should be different. HF, F minus, lost a proton. So meaning donated the proton, so that's the acid, that is the base. Because in the reverse reaction, F minus takes a proton to form HF. So they are conjugate acid-base pair. You can even see here acid, base, conjugate acid, conjugate base and conjugate acid, like that. All of these pairs are similar to that. So this is your acids and this is the conjugate base. And then this is the base and this is the acid. So that is the other conjugate acid-base pair. Okay. The following reactions are important. Environmental processes. Identify the conjugate acid-base pairs. H2PO4 minus CO3 2 minus, HPO4 2 minus, HCO3 minus. Now tell me for this guy, what is its other species? H2PO4. So you look for your products. Find out the similar one. So this one, right? These two. It's obvious. H2PO4 minus, HPO4 2 minus. What happened over here? There are two hydrogens. There's one hydrogen. So these are going to be your conjugate acid-base pair. So which one is the acid going to be? Remember, acid is a proton donor. So there are two here, one here. So donated the proton. So this is the acid. So then this is the conjugate base. What about carbonate? So here you have CO3 and HCO3. Number of hydrogens increased. So then this is going to be your base and this is going to be your conjugate acid. So that is the conjugate acid-base pairs. Carbonate and bicarbonate are conjugate base acid pair. H2PO4 minus and HPO4 2 minus are conjugate acid-base pairs. So the next one, water OH minus, hydrogen oxygen, oxygen hydrogen. And then the other one SO3 2 minus, HSO3 minus. Now between water and hydroxide, tell me which one is the acid, which one is the base. Is water acid or base? How do you know? You look to see if the number of hydrogens increased or decreased. There are two on water, one on OH minus. So the number of hydrogens decreases. So then this need to be your acid and this is the conjugate base. And sulfite, SO3 2 minus, HSO3 minus. Number of hydrogens increased. So then the proton acceptor. So this is the base. That is the acid for that conjugate acid-base pair. Okay. That's how you identify conjugate acids and bases. It explains over there. Now we see all of these examples we have seen. this reverse reaction also, reversible process. How do you know where does the net reaction take place? Is it going to go forward or is it the reverse reaction? So the net reaction direction. Let's see how to figure that out. The net direction of an acid-base reaction depends on the relative strength of the acids and bases involved. A reaction will favor the formation of the weaker acid and base. For example, now you find, remember we saw acids and bases in both sides. So you have an acid and conjugate base, base and the conjugate acid. So basically in your reactant side also you have acid base, and your product side also you have base and an acid. So which direction would it favor? Normally a reaction would favor reacting of stronger acid and stronger base to give you weaker base and weaker acid. That way is the net direction of the reaction. Okay. So this particular reaction where you have H2S and ammonia giving you HS minus and ammonium ion, this is a stronger acid, stronger base, weaker base and weaker acid. So the reaction favors the formation of the products. But in this particular example, it is written here, this is a stronger acid, this is a stronger base. But how do we know that? So by looking at a chart that tells us what is the strength of conjugate acid-base pairs. Okay. The stronger the acid is, the weaker its conjugate base. If you have a very strong acid, its conjugate base is going to be weaker. When an acid reacts with a base that is further down the list, the reaction proceeds to the right. So Kc going to be greater than 1. When an acid reacts with a base that is further down the list. Now these are your acids. If it reacts with a base that is further down the list, the reaction proceeds to the right. So basically we have to look up what is the strength of acids and the base that involve. We can do that by looking at few examples. Okay. So these are the acids. When it reacts with a base, somewhere here, that proceeds to the right. Because if you see here, this is the acid strength. From going towards this direction, we will see strength of the acid increases. As you go down this list over here, you can see the base strength increases. So basically we find strong acids here and strong bases here. So they react, they always proceed to give you the product since the Kc is going to be greater than 1. Okay, predict the net direction and whether Kc is greater or less than 1 for each of the following reactions. Assume equal initial concentrations of all species. So we have these ones. First we can find out whether they are acids or bases or whether they are stronger or weaker. H2PO4 minus, HPO4 2 minus. Let's see, between these two, this is going to be your acid. And this is going to be your conjugate base. Remember, there are 2 hydrogens, 1 hydrogen phosphate. So that is the conjugate acid-base pair. And on the other hand, we have ammonia going to be your base. And then NH4 is going to be your acid. Remember, the number of hydrogens increase 3 and 4. Now we have to see, we have 2 acids and we have 2 bases. What are their acid strengths? So let's look at the 2 acids. H2PO4 minus. So this is an acid, this is an acid. H2PO4 minus and ammonium ion. Between those two, which one is the strong acid? Okay, we have to refer to our table. Okay, now we have to locate H2PO4 minus. Where is it? H2PO4 minus. And then where is the other acid, ammonium ion, NH4 plus. NH4 plus. Do you see here? These are the two acids. Okay. H2PO4 minus and NH4 plus. So those are the two acids that we have identified in our reaction. So between these two, which one is a strong one? Remember this thing is a strong one because it's higher in the list. And then the two bases we have are ammonia and HPO4 2 minus. Now let's look at in the base side, where is ammonia? Ammonia is here. And HPO4 2 minus, HPO4 2 minus right there. So between these two, which one is a strong base? Remember the base strength increases. So ammonia is the strong base. So if you have ammonia, and then the strong acid would be H2PO4 minus. So these two will combine to give you the weak acid and the weak base. So the weak acid is NH4 plus, and then the weak base is HPO4, these two, right? So then, which direction do you think the reaction would proceed? The strong base, we just found out from our table, ammonia is strong base and H2PO4 also strong acid. So the strong acid and strong base will give you weak acid and the weak base. So the reaction will proceed to the right direction. So Kc would be greater than 1. Okay. Similarly, we can do the next one. Water HS minus combine to give you hydroxide and H2S. And let's first figure out the conjugate acid base pair. Now water going to be H2O becoming OH minus. It's losing a proton donor. So this is your acid. This is the base. HS minus H2S accepting a proton. So this is the base. This is the acid. Okay. Then you're going to look at the two acids. Which one is a strong acid? And our two acids are water and H2S. Let's go back to our table and see between water and H2S, which one is the strong acid. Now where is water? So we're going to look at our acid section because we figured water and H2S are acids. Okay, so where is water? Water is here. Where's the H2S? Over here. Now between these two, which one is a strong acid? It's H2S, right? Let me show you your reaction. HS minus OH minus plus H2S. Now between the two acids, this is acid, we identified H2S is going to be the strong acid. I put S for strong, right? And then let's look at from our bases, conjugate bases, HS minus. So you look at in the base section, HS minus right there, and hydroxide OH minus. Which one is strong between these two? It is going to be hydroxide because it's down the list. Excuse me, it's a strong one. So hydroxide. So this is a strong base. So the strong base and strong acid happen to be in the product side. So what did we say when an acid-base reaction take place? Always a strong base and strong acid react to give you weak acid and weak base. So this is your weak acid and this is your weak base. So then the reaction will not go forward, but the reverse reaction will take place. If the reverse reaction is going to take place, so then the Kc is going to be less than 1. If it goes to the right, Kc would be greater than 1. Okay. Alright, so then stronger base and stronger acid will give you weak acid and weak base. The net reaction for this reaction is to the left and the Kc would be less than 1. So that's how you predict which direction a reaction proceed if you are given a strong acid and a strong base, or a weak acid and a weak base. Okay, first thing is you need to figure out what are the conjugate acid base pairs, and then you compare the two acids and the two bases and figure out which one is a strong one. Always a strong acid and strong base gives you the weak acid and the weak base. Okay. Maybe we'll start solving problems involving weak acid equilibria in the next session.